Okay, welcome to lecture 3. So, what we have studied so far? So far we have talked about definitions of AI, we talked about agents and its type of agents. Then we talked about something called PEAs, performance measure, and the task environment change. After that, we talked about how to model AI problem as a research problem, and we also talked about a general approach for that key. We talk about general approach to solve that problem. So in today's lecture, in the lecture 3, we'll dive into this specific algorithms or specific search algorithms to search for the solution in our state space graph. So we'll start with the a search algorithm called BFS. So BFS stands for breadth first search. I'm pretty sure आप लोगों ने ये नाम पहले भी काफी सुना होगा in your other courses like data structures के कोर्स में या फिर algorithms के कोर्स में भी. So yes, this is the same algorithms BFS will जो कि ग्राफ में किसी पाथ को फाइंड करने के लिए यूज आती है and we'll talk about that algorithm only. So after we talk about the BFS, how does it works and how it can help us in finding the solution. Then we'll talk about how can we compare to such algorithms because since the BFS is there, DFS is there, then UCS. So how can we compare those various search algorithms? क्योंकि आपने जैसे algorithms का course किया, then there you discuss about something called time complexity, right? Complexity, or another thing that you discuss about space complexity. So these were two measures of comparing two algorithms, right? जैसे आप लोगों ने बिगो नोटेशन के बारे में पढ़ा होगा. So all these things we'll talk about here also. What are, how to compute time complexity, how to compute space complexity, but in a little bit different manner because the graph on which we are working or the graph on which we are running our search algorithm, it's quite different from the graph that you have seen in your data structure course or algorithms course. We'll talk about these subtle differences between these two state space graph and a normal graph and how an algorithm working on the state space graph behaves something differently or how to compare the performance of these algorithms. We need to come up with some certain other criteria which other than or the criteria will be same, the time complexity and space complexity, but how to compute them is quite different because the graph representation is something different in the air or in our state space graph. So we'll talk about these later. But let's first talk about the BFS or the breadth first search and how does it works and all. So remember in the last lecture we talked about this general search strategy, right? So what was the general search strategy? Start with the frontier or also known as a something called open list. So by the name open list, you can think of this name in such a manner that any node which is being inserted in the frontier can also be removed from the frontier. So you can that's one concept you can use for the name open list. But simply it's a list or data structures जिसके implementations के बारे में हम will talk about specific implementation or specific data structures to implement the frontier. We'll talk about when we talk about specific search algorithms. So we'll start with the frontier, which only contains the initial node or initial state. We'll also maintain an empty explored set or visited set. There is another name for it, visited set, or something called closed list. So again, the name closed list can signify that if once one node is being added into the explored set, it cannot be removed again. So once added, can't be removed, because हम node कब add कर रहे हैं? We are adding a node into the frontier, sorry, in the explored set when that node has been explored and we have added its successors to the frontier. So now there is no more role of that node. So we are adding into the explore set ताकि अगर वो node फिर से कहीं किसी और node की वजह से explore हो रहा है तो we keep track कि ये node already explore हो चुका है and we don't want to visit it again. So the endless cycle that we talked about in the last class should not be repeated here. So that's why we are maintaining this explore set. So what's the strategy? We'll maintain these two frontiers. Then we'll simply keep repeating. So it's a loop. So all these steps should be done in a loop. We'll check whether frontier is empty. If frontier is empty, then we'll return no solution. If we have found no solution, we have explored all the possible states. We have searched for them, and but still haven't found the goal state. So that means haven't found goal state. Found path till goal state. Okay. If it is not empty, then we'll simply remove one node from the frontier. Remove node. Check whether this is a goal node or not. If it is a goal node, then return the solution because we have found the goal node. So what is the solution? Solution is simply the path till goal node. Till goal from start. If it is not a goal node, then what we'll do? We'll add that node to the explore set because now its purpose has been fulfilled and we just want to make sure that we don't add this same node into the frontier again in the future. So we'll keep adding into the explore set. Then we'll expand the node. What do you mean by the expanding the node? We'll simply, by expanding node, we only means कि node in उसके जो भी successors है, जो भी successors आए हैं S1, S2, S3, add those into frontier. अब पहले तो हम क्या कर रहे थे, सबको ऐड कर रहे थे, बट नाउ विल मेक श्योर कि जो सक्सेसर्स आए हैं S1, S2, S3, these are not in the frontier already, because अगर already frontier में है तो what's the point of adding them again, right? And so they aren't in the frontier already, or they are not in the explored set either, because explored set में जो nodes है, that means there has been explored already, so we don't want to go over those nodes again and again. So we'll check whether जो भी ये frontier में भी नहीं होने चाहिए and explored set में भी नहीं होने चाहिए. तो अगर ये दोनों में नहीं है, that means कि this is something a new node which algorithm has found, and let's explore this one. A new path or new node, new state has been generated. So that's only when we'll add it to the frontier. Okay, so now that we know about the general approach, let's go over this for the BFS or this like let's talk about the breakfast algorithm. So what happens in the BFS? So this general strategy is same, but only so BFS uses this frontier as a queue. तो क्यू डेटा स्ट्रक्चर्स के बारे में आपने पढ़ा होगा. So what is a queue data structure? Queue is simply, what is queue? Queue is simply a data structure which is more like a queue. तो जो नोड क्यू में पहले ऐड होता है दैट इज रिमूव फ्रंट पहले फ्रॉम द फ्रंटियर. तो व्हाट इज लाइक दिस कि जैसे मान लो मेरे पास सीक्वेंस ऑफ एक सीक्वेंस आ रही है कि देयर इज अ सीक्वेंस ऑफ कमांड्स दैट आई एम रिसीविंग कि इट इज मोर लाइक कि add 2. So this is the first command, so I have added 2 into the frontier. Then there is this command add 5, add 5. Then there is this command remove. So whenever there's this remove, what we'll do, we'll simply remove the first item into the queue. So this is known as the front of the queue, and this is known as the rear or back of the queue. So we'll keep inserting at the back, insertion, and we'll keep removing from the front. So this is how queue works. So we'll simply remove one node. For example, remove 2. So remove, you don't need to specify 2 because queue से जो removal होगा वो सबसे पहले वाला node ही होगा, not any other node. So only node that can be removed is जो front में 2. Then again, if I receive another command like add 6, that means I'll add insert 6 into the footer. Then if I remove, again remove command, then what I will do, अब कौन सा है जो remove हो सकता है, 5, तो remove 5. If I again receive another command remove, then I'll again remove 6, right? And if I again receive the remove command, then what? Now queue is empty, so nothing can happen, right? This will give us error key, or this will result in error or buff overflow or memory segmentation fault, something like this, depending upon how we are implementing, or exception, because there is no any other node. So this will be the scenario when we'll return kill, there is no solution. Or if now again if you remove found add 7, then you'll again insert 7 here, then so. So this is how queue works. So you get remove items from the front and insert item at the back. And you realize कि क्यू का जो टाइम कॉम्प्लेक्सिटी है हर एलिमेंट का और हर ऑपरेशन का, तो क्यू वर्क्स विद द ऑर्डर 1 टाइम कॉम्प्लेक्सिटी. Both insertion and deletion. तो क्यू के लिए both insertions and deletions takes the order 1 time complexity. That's the one of the biggest advantage of the queue. They have insertions and deletions are fixed. Insertion can happen at the back of the queue and deletion can happen just from the front of the queue. And because of this fix, there is no a particular sequence is maintained कि this node is entered first, तो यही remove होगा पहले से. तो because of this nice property, the time complexity for operations like removal, deletion, removal, insertion, these can be defined in an order 1 time complexity. So there are various examples of the queue that you must have seen in the real world also, like the line जो किसी भी जगह पे लगती है, जैसे बैंक वगैरह के लाइन या फिर मेस में फूड लाइन्स एंड ऑल दिस. यहाँ पे वह क्या भी होता है, जो लाइन के सबसे पहले खड़ा है दैट गेट्स द सर्विसेज फर्स्ट. आफ्टर दैट उसके बाद वाला, उसके बाद वाला, और जो भी कोई नए आ रहे हैं वो दैट गेट एडेड इनटू द एंड ऑफ द लाइन. So this is one. So let's use this properties of the queue and implement our frontier as a queue, and let's see how the algorithm works. Everything else is same, just the frontier that we are using is now working as a queue. So let's run our BFS algorithm on this same example that we are talking about. So now this, what is this frontier? So this frontier is now queue. So queue, there is another name for queue, and they called FIFO, or what is this FIFO stands for? This FIFO is first in, first out. मतलब जो सबसे पहले क्यू के अंदर गया वही सबसे पहले बाहर आएगा. तो दिस क्यू इज ऑल्सो नोन एज FIFO, FIFO डेटा स्ट्रक्चर और FIFO फ्रंटियर. तो नोड जो पहले इंसर्ट होगा दैट विल बी removed from the frontier first. Okay, so let's, the general strategy we all know. We'll start with the frontier containing the initial state. So what's the initial state? A. This is our initial state, and this is our goal state. So let's insert, this is our initial position of the frontier. Now what we'll do, we'll repeat. What we'll repeat? We'll check whether the frontier is empty or not. If it is empty, then we'll return no solution. So let's check whether frontier is empty or not. No, it's not empty because there is A inside the frontier. There is one particular node inside the frontier A, so will not. So it's not empty. तो अगर empty नहीं है तो what we'll do? We'll remove the node. So let's remove the node. Let's remove A. What we'll do after removing the node? What's the step? If node contains, remove a node from the frontier. Remove कर लिया. And for, since we want to explore, check it again, we'll simply store it in a data structure, a variable time. Now what? If node contains a goal node, then return the solution. Check whether this is a goal node. So is temp equal to E? No. So we'll again continue. Agar it is yes, then we'll return the solution. Return solution. But since it is not, so we'll simply what we'll do, add it to the explode set. A को explode set में add कर दिया, and we'll expand the A. What do you mean by expansion? A के जो भी neighbors है, which is B, that will be added into the frontier. So before we add B into the frontier, we'll check whether this is B is on in the explode set or frontier. So not in, only if added into the frontier, only if not in frontier or explode set. ठीक है, तो is it B in the frontier or explode set? No. So we'll add B into the frontier. So let's add B into the frontier. Now what? Now we'll keep repeating this. Check whether frontier is empty or not. Since frontier contains B, it is not empty. So we'll remove the node from the frontier. Check whether, so now what? Temp is equal to B. Is it गोल नोड नो, तो विल कंटिन्यू विद दिस। तो होगा क्या, एड बी इनटू द एक्सप्लोर सेट एंड एक्सपेंड द बी। तो अगर एक बी को एक्सपेंड कर रहे हैं तो क्या होगा, बी के जो भी नेबर्स है, बी के नेबर्स कौन कौन से, सी एंड डी, that will be added into the frontier only if not in frontier explore set. So are these in explore set or frontier? No, so they will be added into the frontier. So let's add C first and D first. Now again remove the node from the frontier. Now there is a two choices, right? तो अगर two choices है तो what should we do? But we know that कि two choices, कितनी भी choices हो, जो अपना फ्रंटियर है वो क्यूज की तरह इम्प्लीमेंटेड है। क्यू की तरह इम्प्लीमेंटेड है, दैट मींस कि जो पहले आया है वो पहले रिमूव होगा। तो अभी पहले कौन है क्यू में, अभी के लिए दिस इज योर क्यू लुक लाइक, तो दिस सी विल बी रिमूव फर्स्ट बिकॉज दिस इज द फ्रंट ऑफ द क्यू, राइट। सो इट विल, अगर आई ड्रॉ मोर एक्यूरेटली, दिस विल लुक लाइक दिस, तो दिस विल बी रिमूव फ्रंट बिकॉज दिस इज द फ्रंट। तो लेट्स रिमूव सी, तो लेट्स रिमूव सी। तो अगर सी को रिमूव किया तो डी विल कम है इस, तो सी, राइट, तो सी को रिमूव कर दिया। नाउ लेट्स ऐड, इज इट अ गोल नोड, नो, तो व्हाट वी आर गोना डू, विल ऐड इट टू द एक्सप्लोर सेट एंड विल एक्सपेंड इट। एक्सपेंड करने के लिए क्या करना पड़ेगा, सी के जो भी नेबर्स है, लेट्स डू दोस। तो सी के कौन से नेबर है, ई, is it E in explore set or frontier, no, so let's add E into the frontier। सी, हम जो गोल नोड है वो फ्रंटियर से निकालते टाइम चेक कर रहे हैं, नॉट व्हाइल इंसर्टिंग इनटू द फ्रंटियर। दैट्स मेक श्योर दैट, क्योंकि ई जनरेट हो गया लेकिन ई अभी तक हम चेक नहीं किया कि वेदर इट्स अ गोल नोड और नॉट, बिकॉज गोल नोड हम फ्रंटियर से रिमूव करते टाइम वो कर रहे हैं। नाउ रिमूव डी, रिमूव डी, इज इट अ गोल नोड, मतलब तो इफ यू रिमूव डी it will be temp equal to e, no, so we'll add d into the explode set and what we'll do, explore d। तो अगर d को एक्सप्लोर कर रहे हैं तो क्या होगा, d और उसके जो भी नेबर्स है which is f, this f will be added into the frontier since because it is not in the explode set or frontier set। So let's add f into the frontier। Now what, again we'll keep repeating the process, remove e, e को रिमूव करते हैं, तो e को जैसे रिमूव किया, now this path will become true and जैसे ये path, that means कि we have found the solution, we will return the solution। solution क्या होगा, a b c e, और जो e है वो c के थ्रू ऐड हुआ है, तो this will be our solution। and as you can see, and this will terminate the algorithm itself because जैसे solution मिल गया, terminate the algorithm or terminate the search, which we don't want। जैसे solution मिल गया, we don't want to continue our search, so this node will never get explored or it will always remain frontier। So this is how BFS works. It uses the queue as a frontier and visited set can be is just a set। You can implement this however you want because there is no, we are not removing it, we are just simply inserting one element into the visitor set। Okay, let's do another example of this। So remember our favorite example of Romania, let's do that for our BFS। and तो यहाँ पे what's the initial state, this is our initial state, and this is our goal state. Okay, so let's run the BFS on this graph and see if we can work with it. Okay, so let me reduce the size a little. Okay, so let's maintain our frontier. So what is our frontier? Q. So this is my Q frontier, and let's maintain a visited set also. Okay, so let's go with this one. Apart from these two, let's maintain something called search tree itself. So I'll talk about this search tree a little later. It's like generating the path itself. Will we this we are using to keep track of the path. So what's the general search strategy? Insert initial state into the frontier. So what's the initial state? Arad. Let's represent it as A only. So this I'm using the capital A for the Arad. So जो भी cities के नाम है उनका first letter I'm using for these steps ताकि ज़्यादा space ना लगे. What will do? Remove the node from the frontier. A को remove किया. Check whether this is a goal node. So temp equal to A. Is it a goal node? So if temp equals to B, return solution. Else explore temp. यही करना था. So we have removed A from the frontier. Okay, this is the front of Q and this is the back of Q. अब अगर temp नहीं है और goal node जो node remove किया that is not a goal node, so what will do? Add that to the visited set. So add A to the visited set. So let me add A to the visited set, and since we have explored A, let's draw our tree here. A has been explored. Now what we need to do? एक के जो भी सक्सेसर्स है तो एक को जो एक्सप्लोर कर रहे हैं तब क्या करेंगे? एक के जो भी सक्सेसर्स तो एक के सक्सेसर्स का क्या क्या है? एक के सक्सेसर्स है ये वाला पाथ, इस पाथ से जो भी आ रहा है ये दिस पाथ and this path. So these are the only three actions possible. Or so successors are S, T, and Z. So let's insert them into the alphabetical order itself. तो सबसे पहले क्या इंसर्ट कर सकते हैं? S, then T and Z. Now we'll repeat the process. We'll check whether frontier is empty or not. Frontier is not empty. We'll remove the one node from the frontier. Since it's a queue, we'll remove the first node itself. So we'll remove S is dot. Now this our temp will become the S. Now is temp equal to B? नहीं. So we'll explore the S. The explore करने से we'll simply add it to the explore set. Right. And since ये S किसकी वजह से add हुआ है? A की वजह से, तो we'll add it to the search tree also. Like this. ये A की वजह से ये हो रहा है. And let's explore S now. तो S की वजह से क्या क्या add हो रहा है? तो एस की वजह से ऐड होगा एफ आर ओ एंड ए, बिकॉज ये चार चार सक्सेसर्स है इसके, राइट। तो अगर आप जैसे एस के बाद में ट्रेवल करोगे तो दिस इज द वन सक्सेसर, दिस इज द वन सक्सेसर, दिस इज द वन सक्सेसर ऑफ द एस, एंड दिस ए इज आल्सो वन सक्सेसर ऑफ एस, बिकॉज एस से आप ए पे वापस भी जा सकते हो, राइट। नाउ check for f, is f in the visited set or frontier? No. So let's add f into the frontier. F has been added. Let's check. Let's check for, right. So let's go into the alphabetical order itself. So that will make it more sense. So let's check for a first. A is in the visited set. Yes, A is in the visited set. Not in Q. तो Q से तो remove उसका, but visited set में अभी भी. तो A will not be added. F, yes, F will be added. O, O is not in visited set and not in the queue, so O will be added, and R, R will be added. Okay. Now again do the same thing. अब क्या होगा? Let's remove another node T. T remove हुआ. अब ये T किसकी वजह से ऐड हुआ था? A की वजह से ऐड हुआ था, right? So we'll insert it to the our plot or tree of T, or let's explore, insert it to the visited set, right? Or तो T को अगर एक्सप्लोर करने गए तो T के क्या क्या ऑप्शन है? T से there are two options connected, A and L. तो A और L. A को चेक करते हैं. We'll realize कि A is in visited set, तो A will not be added. Let's check L. L is not in visited set and not in frontier itself, so L will be added. So let's add L into the frontier. Right? Now what? Remove Z. So let's remove Z. So is Z equal to B? No. So we'll explore the Z. So explore करने से क्या होगा? Z will be added here and Z will be added here because Z was added using A. And to explore Z, we simply need to do what? Z के जो भी neighbors है, तो Z के कौन कौन से neighbors है? Z has two neighbors, O and A. तो A और O. Let's check O. So let's check A. A is already in visited set, so we'll not add it again. O. Let's check O. O is all. O is not in visited set, but O is already in queue, so it will not added again also. तो Z की वजह से कोई और नोड ऐड नहीं होगा. Good. Now let's add F. F ऐड किया. Let's remove. So F is not equal to B, so we'll have to explore it. So let's add it to the visited set. And ये F किसकी वजह से ऐड हुआ था? S की वजह से. तो let's insert it to the after S only. And if we explore it, F के क्या क्या successors है? F has two successors, S and B. So B and S. So now this So we'll add is we'll check for B. Is it in visited set or Q? No. So we'll add it to the frontier. We'll add it to the frontier. But so let's add B. S is already in visited set, so it won't be added into the frontier. Again, remove O. O किसकी वजह से ऐड हुआ था? O was being added using S. So let's add it to the. So let's explore O, add it to the visitor set, and let's find out O के बारे में क्या है. If we go over O, okay, कौन कौन से नेबर्स है? Z है और S है. तो S and Z. अब S is already in visited set, so it will not be added, and Z is also in visited set, it will not be added. तो O की वजह से कोई ऐड नहीं हुआ. So let's remove the next node R. R किसकी वजह से ऐड हुआ था? S की वजह से. तो let's explore it. It's not equal to B, so let's explore R. If we explore R, then what's going on? R के क्या क्या successors है? R has three successors, S, P and C. So C, P, S. We'll check for C. Is it not? Is it in the node or anywhere? No. So we'll add C into the frontier. So let me simply remove these nodes which have been added in the frontier and so L and B. So let's move these nodes from the front and the L and B. So C नहीं है, तो let's add C into the node. P भी नहीं है, तो let's add P into the node frontier. S is already visited, so S will not be added. So this is the R. Let's remove L. Let's remove L. L को remove किया तो क्या होगा? L किसकी वजह से ऐड हुआ था? L was added because of the T. So let's add L को visited मार्क करते हैं and T केस में L ऐड किया जाता है. Let's make L visit explore L. L के कौन कौन से successors हैं? L has only two successors, T and M. So M and T. Let's explore M. So M is not in visited and not in Q. So M will be added, but T will be not added because T is already in visited. So that's it. Let's repeat the process. Remove B. Now since remove B, and now this B was added because of the F, so you can add it to B here, and we realize that B has this. Now this condition has been satisfied, so we'll return the solution. So how do we generate the solution? That's where our this path will help us. So solution is simply B से start करके you can go upward till the initial state and जो path आया that is solution. Solution is A, S, F and B. So this is the solution returned by our algorithm. As you can see, there are still lots of nodes in three different tier and they will not be in explored because जैसे आपको goal मिला, your algorithm will terminate and return the solution. So this is how BFS actually works. Okay. Okay. So now that we know about this BFS and DFS, how can we come? So if I, let's, what are the properties of this BFS? What are the various properties of the BFS? So this, so let's talk about those. So we have talked about BFS algorithm, right? Search algorithm. And जब भी आप किसी algorithm के बारे में बात करते हो तो we need to find out some things about the algorithm, some properties about the algorithm, which makes it better or worse compared to the other algorithms, right? जैसे अगर दो algorithms है A1 and A2, how will you compare A1 and A2? You define some criteria like time taken by A1, time taken by A2, space take, space consumed by A1, space consumed by A2, and so on. So there are some criteria that you define compared to algorithm. So let's define those criteria here also. So the two criteria that we'll define is already you have already seen time complexity and space complexity. But apart from these, we'll define two more criteria: completeness and optimality. So what are these criteria and why? What does these represents? So to talk about that, let's first talk about what's the issue or what's the main difference between graph and state space graph. So we need to talk about these two things before we talk about these optimality, completeness, and etc. So what's the difference? So graphs that you have discussed so far in the data structures course or in algorithms course, those graphs are given to you as an input. The entire graph is given to you as input. So the entire graph is given as input. But state space graph, the graph might be too large. Entire graph might be too large because we might be discussing a problem which has the infinite number of states or exponential number of states. So this entire graph cannot be given to you. You are only given a state and a transition function. तो जो input यहाँ पे मिलता है that is state and a transition function. So we generate our graph based on this. So we generate our state space graph using an initial state and the transition model. So we are never given the entire space graph, so we can't, so we don't know the number of nodes into the graph. number of edges in the graph. So if these are not given, so it is hard to compute the time complexity in terms of number of edges, number of nodes, so on, of the graph itself. So we तो हो सकता है कि जो even though in this entire state this graph might be too large, our algorithm only explores a fraction of the graph. That means we, even though state space graph might be too large, our algorithm will just explore few nodes or few states, not the entire graph. But in this case, entire graph might be explored. Explored as graph is small enough. बट अगर मैं अपने के एआई के केस में स्टेट स्पेस ग्राफ को अगर पूरे ग्राफ को एक्सप्लोर करने चले जाए तो एल्गोरिथम विल टेक इनफाइनाइट algorithm might even take infinite amount of time. So that means कि we can't just go using the like number of nodes कितने graph में, because we don't know that exact criteria or exact count कि कितने nodes है. So we can't define our time complexity in terms of number of nodes in the graph or so that's where that's why we will define a separate criteria or these completeness, optimality, time complexity, stress complexity in a separate ways compared to what you have seen in the traditional approach. जैसे traditional में V plus E is the time complexity for or M plus N for BFS DFS. So V is the number of vertices, number of nodes, and A is the number of edges. But we don't know here the number of nodes, number of edges, so we can't use these criteria to define our time complexity and stress complexity here. And since our entire state space graph might be too large कि हो सकता है कभी कभी एल्गोरिथम हमारी सॉल्यूशन रिटर्न भी ना करे and it stuck on a infinite loop. So that's where this completeness property helps us. This will define key whether one algorithm actually returns a solution or not in a state space graph. Right? Because if a state space graph is infinite or too large, then algorithm might take lots of time, keep searching into the state space and never returns to a solution. So if algorithm is complete, then we say that it will return a solution in finite amount of time. But if it's not complete, then means we can't guarantee. It might return the solution for some state space, but it may not return the solution for some state space graphs. So, but if it is complete, then it is bound to return. We are kind of like guaranteeing something. Ki algorithm will return a solution in the given or finite amount of time in every possible state space graph. So that's why this completeness property comes in. And the optimality property, since the path that has been returned by the algorithm, it might not be the shortest path so that we have defined using the path cost function. It might be a different path compared to, or there might exist another path which might have lower cost compared to the other solutions. So this optimality will define the optimality in terms of the optimal path or the path which has the lowest cost. Because remember कि जैसे हमने जब AI agents के बारे में पढ़ रहे थे, our goal was कि utility based agents they always try to maximize their performance measure. So now this performance measure can be maximized when we find the optimal path. So now our AI agent will try to find a path which is optimal or much more better compared to the other paths, kind of like the quality or ability to find the best path possible. So that's why if an algorithm returns the best possible path, which is the lowest cost, then we say that the algorithm is an optimal algorithm. But if it doesn't return that, then we say that an algorithm is not optimal. So that's why these four criteria we'll use to define or compare the properties of various search algorithms. Okay, so we'll define the completeness, optimality, time complexity, and space complexity. So we know the completeness, whether either algorithm returns a solution in finite amount of time. And we are saying key algorithm returns a solution only if the solution exists or reachable. If solution is not reachable, then how can algorithm even return the solution? So this completeness property defines whether algorithm can even return the solution or not. Optimality property, this defines the solution returned by, okay, let me write it somewhere else. Let me write it here. Solution returned by algorithm is optimal or not. What is optimal? As I would say, what is an optimal solution? This is the solution or path with lowest cost. Okay, so this is time. So now that we can, now that we know how to define completeness, how to define optimality, how do we compute the time complexity? So let's talk about the time complexity and space complexity. So technically time complexity क्या होगा? Number of, so this is the number of states space nodes generated by the algorithm. So we'll define our time complexity in terms of number of nodes, कितने number of nodes generated by the search algorithm. Why? Because मान लो कोई algorithm n nodes generate कर रही है, generated, तो n nodes किसी algorithm ने generate किया, तो मतलब n states explore किए हैं इस algorithm ने solution को find करने के लिए. तो, तो कितना टाइम इसने लिया होगा टोटल? तो टोटल टाइम लेने के लिए क्या होना, मान लेते हैं एक नोड को जनरेट करने के लिए टाइम लगा होगा सी अमाउंट ऑफ टाइम, सी amount of time to generate one node. तो टोटल कितना टाइम लग जाएगा? अगर एक नोड को जनरेट करने में सी अमाउंट ऑफ टाइम लग रहा है और टोटल n नोड जनरेट हो रहे हैं, तो टोटल टाइम विल बी n times c. This will be the total time taken, and since c is the constant, this is a constant. If we represent it in a big O notation, we can simply say that the total time will be big O of n, because big O notation removes the constant. So we can see the time complexity can be represented using in terms of number of nodes generated by the algorithm. Now we need to find out कि कितने nodes generate हो रहे हैं. Simply with the same logic we can say space complexity is also same, because the number of states plus nodes stored by algo in frontier or visited set, right? So space complexity, तो space algorithm कहाँ पे ले रही है जब it is exploring the nodes, right, when it's exploring the set. So, oh sorry, when it's storing, so what's the space consumption of this algorithm? The space consumption is computed by the कितने nodes और कितने states को algorithm को store करना पड़ रहा है frontier में और visited set, because those are the two data structures that we are using repetitively in the algorithm. So the space will be computed like this. So let's see exactly कितने nodes और कितने टाइम कितना ले रहे हैं, कितना वो nodes. तो how can we calculate? The question is how to find out the number of nodes generated by a search algorithm. So how do we find this कि node कितने generate हो रहे हैं? That's a good question, right? So let's try to find this solution of this or answer to this mystery question कि कितने nodes generate हो. Okay, तो hmm, let's think like this कि how does algorithm work? It starts with the initial state. So this is the initial state, right? So initial. अब इस initial state को तो how the DFS क्या करता है? तो DFS में सबसे पहले क्या होगा? This is sorry BFS. How does BFS work? This is my frontier. तो frontier में initial state होगा. तो initial state से क्या होगा? It will get removed. And जैसे ही इसको remove करेंगे, will explore that state. तो explore करेंगे तो क्या होगा? तो एक्सप्लोर करने पे जो इसके पॉसिबल स्टेट्स थे, जो सक्सेसर स्टेट्स थे, वो जनरेट होंगे. तो लेट्स सपोज कि इसका सक्सेसर स्टेट्स आर S1 S2 एंड SB. B successor states. So all these will be added into the frontier. So S1 S2 SB will be added into the frontier, right? So now what? अब क्या होगा? S1 रिमूव होगा एंड अगर वो सॉल्यूशन है तो वो रिटर्न हो जाएगा, अदरवाइज उसके जो भी सक्सेसर्स है वो ऐड होंगे, राइट? तो S1 के सक्सेसर्स क्या होंगे? लेट्स ऐड दोज सक्सेसर्स आल्सो. तो S1 के सक्सेसर्स क्या होंगे? S11, लेट्स सपोज S12 एंड लेट्स सपोज कि for the worst case scenario we are assuming, so S1 also has the B successors. Well, we can since जब भी हम टाइम कॉम्प्लेक्सिटी वगैरह कैलकुलेट करते हैं, टाइम कॉम्प्लेक्सिटी और स्पेस कॉम्प्लेक्सिटी, वी ऑलवेज कंसिडर द वर्स्ट केस सिनेरियो, राइट? कि वर्स्ट पॉसिबल केस क्या हो सकता है कि, तो वी technically we are trying to find out the worst number of or maximum number of nodes which can be generated by the algorithm. So let's suppose कि हर algorithm का हर स्टेट पे b possible actions है, so this will generate b. Similarly s2 will generate b successors, so s21 2 s2b, similarly sb1 2 sbb, and we can keep doing this, right? We can keep doing this, so this will do something like this, and this will keep doing this until we found the goal. So technically देखा जाए तो यहाँ पे this can be considered as a level 0, this can be considered as level 1, level 2. So the BFS explores the search space in a level by level manner. तो let's suppose कि उसे जो goal मिला है, that goal has been found on the level D. D लेवल पे जाके उसे गोल मिला है, अगर डी लेवल पे जाके गोल मिला दैट मीन्स कि उस तक कितने नोड्स जनरेट हो चुके होंगे, वो टोटल नंबर ऑफ नोड्स होंगे, राइट? बिकॉज तब तक तो दिस एल्गोरिथम विल कीप जनरेटिंग दिस सीक्वेंस ऑफ नोड्स, राइट? तो what are these, what's the number of these nodes? So let's try to get an estimation of that on that. तो यहाँ पे कितने नोड्स है? ओनली वन. यहाँ पे कितने नोड्स है? बी. यहाँ पे कितने होंगे? क्योंकि ये बी नोड्स है, ये अगेन बी नोड्स है, एंड टोटल से ये भी बी, तो बी टाइम्स बी नोड्स होंगे यहाँ पे, जो कि बी स्क्वायर. यहाँ पे सिंपली बी टाइम्स बी स्क्वायर नोड्स होंगे, जो कि बी क्यूब, एंड इफ आई कीप कंटिन्यू दिस, इस लेवल पे होंगे बी टू द पावर डी नोड्स. तो दिस गॉट द पॉइंट कि इनिशियल स्टेट पे सिर्फ एक नोड था, उस पे बी, क्योंकि बी पॉसिबल मूव्स है, उसके बाद उससे बाद हर बी नोड के पास, हर नोड के पास बी और नोड पॉसिबल मूव्स है, तो बी और सक्सेसर्स है, एंड देयर आर टोटल बी सच नोड्स, तो बी स्क्वायर सक्सेसर्स विल बी जनरेटेड. सिमिलरली यहाँ पे बी स्क्वायर सक्सेसर्स है, तो इन हर सक्सेसर के बस बी पॉसिबल मूव्स है, तो ये बी एंड ऐसे टोटल बी स्क्वायर ऐसे बी है, तो बी क्यूब. एंड इफ वी टोटल सम इट अप ऑल द नोड्स जो भी है, इफ वी टोटल नंबर ऑफ टोटल नोड्स मुझे फाइंड करना है, which will be 1 plus b square plus b cube b to the power d, right? So in this FGP you can find the sum, and if I just simply big O notation में मैं represent करूँ, तो this will be b to the power d. So this will is the time complexity. And since time complexity for of BFS. Okay. So what this B represents, this B is something called, this B is something called branching factor, and the D is the डेप्थ जहाँ पे सबसे पहला गोल नोड आपको मिल रहा है, क्योंकि हो सकता है मल्टीपल गोल नोड्स हो। वी जस्ट वांट कि सबसे पहला वाला जहाँ पे मिलेगा हमें, दैट विल बी रिटर्न्ड बाय एल्गोरिथम। सो क्योंकि जैसे गोल नोड मिला, विल एल्गोरिथम विल टर्मिनेट एंड दैट्स इट। सो द टाइम कॉम्प्लेक्सिटी, तो दिस इज नोन एज द ब्रांचिंग फैक्टर। Why branching factor? Because as you can see, this represents कि कितनी branches spread out हो रही है हर नोड से, कितने हर नोड के कितने possible successor से। तो this can simply represents कि worst number of successors, number of successors for a node. Okay, so this is the branching factor. The D is, तो B हो गया branching factor। तो हम तीन तीन चीजें हम यहाँ पे यूज करते हैं टाइम कॉम्प्लेक्सिटी वगैरह निकालने के लिए। सबसे पहले B ब्रांचिंग फैक्टर, D डेप्थ ऑफ शैलोएस्ट गोल नोड, मतलब कौन सी लेवल पे जाके हमें पहला गोल नोड मिल रहा है, दैट इज द डेप्थ ऑफ शैलो नोड। एंड विल यूज अनदर टर्मिनोलॉजी कॉल्ड M, which is the length of longest path in search space। तो व्हाट इज दिस मीन कि जैसे यहाँ पे D पे मिल गया हमें सॉल्यूशन, बट दैट डजंट मीन कि D इज द लास्ट लेवल, राइट। ऐसा भी तो हो सकता है कि जैसे सर्च स्पेस इज मोर लाइक दिस कि यहाँ पे है दिस इज माय D, बट इसके आगे भी तो सर्च स्पेस है, इनके भी सक्सेसर्स होंगे, राइट। टिल सम लेवल, this till this level is known as M। So M is like a largest level that can be found in a search tree. So this is the M. Why we are going to use it? We'll talk about another algorithm called DFS, which will simply DFS will do. It will take one single path and iterate till the last node. It will go till N. So with this time complexity of DFS is order of b to the power d. We already discussed this. Space complexity of BFS is also o to the power b to the power d, because जब आप इस नोड को एक्सप्लोर कर रहे होंगे इस लेवल को, you need to store all these nodes in the frontier, right? So all these nodes will be added into the frontier in worst case is all nodes of goal level will be added into the frontier at the same time. So that's the time complexity, that's the space complexity. Let's talk about something called completeness property. Is BFS complete? So will BFS always return a solution? And yes, BFS will return a solution, because as long as this branching factor B is finite, हम इस लेवल D तक पहुंच ही जाएंगे जो कि finite है, right? तो अगर B finite है तो we'll keep exploring the levels until we reach the T. So it is complete, yes, only if B is finite. So there might be some problems where B is infinite, this branching factor is infinite, but those are not that much. So in most of the cases, completeness property is there for the BFS. And let's talk about the optimality. Optimality. So let let's talk about the optimality. Let's go over our past two examples of the BFS. यहाँ पे BFS में जो path return किया था वो था A B C E, which was the since technically A की path था, but that was also the shortest path there that was there, right? Shortest path. But यहाँ पे जो path return किया है algorithm ने, that is F to S, S to F, F to B. Is it shortest path? Because इसकी मैं cost निकालूं तो F to S, S to F, F to B, इसकी cost अगर निकाली जाए तो 140 plus 99 plus 211, right? But think about this path. So another path that you need to consider is A to S, S to R, R to P and B. So what do you think? Is it इसके लिए cost क्या होगी? 140 plus 80 plus 97 plus 101, and if I use the calculator, 110, so if I use the calculator or just compute these numbers for you, so what will be these numbers? These numbers will give us the values of, okay, just let me use this, okay, so 140 plus 99 plus 211, it will give us the cost of 450, and if I talk about this, 140 plus 80 plus 97 plus 101, so this will give us the cost 418. So this path is much better than this one. So that means our BFS is not returning the optimal path, right? So BFS is technically optimality. तो दोनों में डिफरेंस क्या हुआ, पहले वाले एग्जांपल में और दूसरे वाले में? Did it return the solution or not? मतलब it returned the solution but not the optimal. तो टेक्निकली ऑप्टिमलिटी जो BFS की है वो डिपेंड करती है कि पाथ कॉस्ट फंक्शन क्या डिफाइन किया आपने. अगर पाथ कॉस्ट फंक्शन यूनिफॉर्म है और यूनिट कॉस्ट है तो यस, BFS will be optimal. So it will be optimal only if path cost function is uniform. But अगर different costs है तो not, otherwise not, otherwise no. So in some cases it can be optimal but not always. So I think I think that's all for today. We'll discuss about the next algorithm called DFS in the next lecture. So see you.